So welcome everybody. My name is Rasmus Bro from University of Copenhagen, and today we have Manny and Barry Weiss and Lyle apparently. No, not really, I guess. But they made this presentation about one of the newest features in PLS Toolbox called Diviner, which is really interesting. So I'm looking very much forward to the webinar. Um, and with that, please, I think Barry, you're starting.
I guess I am.
Okay, thanks.
Okay. And so you've seen that I'm here. So now I'm going to turn my video off and not use up any bandwidth. Okay. And all right. So thanks for coming. We've it's nice to have an audience for this. This is about work that we've been doing over the last couple of years. I think we kind of came up with the concept now about 3 years ago, and it's taken a while for it to come to fruition, but we're pretty much there. Still lots of things to do. And what's the problem? So many models, so little time. That's kind of the problem. Automated machine learning is a possible way out of that. Uh, the diviner approach, which we'll tell you about, is semi-automated machine learning. And we'll talk a little bit about the workflow and show some examples. And then actually it's going to get real fun and real nerdy because we're going to talk a bit about ensemble models. So I think about that point, I'll pass it off to Manny, who's here, Manny Palacios, and have some conclusions. So the problem is that analytic chemists and process engineers often have to build predictive models from complex data, and uh, there are a lot of modeling options. And I kind of have to laugh about that because we, for instance, have added an awful lot of different types of pre-processing to PLS Toolbox and Solo over the years. And that's great, but it is admittedly sort of almost overwhelming, all the different things that you could do. Uh, so there's a lot of choices for learning algorithms, linear and nonlinear methods. There's the meta parameters associated with those. There's all the different pre-processings you could use. There's feature selection. What are you going to do for variable selection? There's a number of ways to choose variables, and of course, they seldom pick the exact same set of variables. So you wind up with a lot of options there, and it's hard to choose the best modeling strategy. Early wrong choices can lead to suboptimal model performance. And of course, everybody's trying to do this with limited staff, including non-experts. And there are some people out there that we see this a lot, for instance, in petrochemical that have to update and make and update an awful lot of models. Some people are fortunate to just have a few that they're looking after, and some people have a lot. So the auto machine learning promise is uh, that we can create this automated machine learning process where machine learning workflows from data processing to model building are all automated. And the objective here is to make the application of machine learning accessible, efficient, and faster, especially for those with limited experience. So AutoML has emerged out of that as data grows in size and complexity. Traditional methods can become time consuming. So AutoML emerged as a way to handle all these complexities in a cost effective way. But, it kind of looks like this here on the bottom, which is you've got the, um, data comes in, you you push the button on the black box for AutoML and the model comes out. If you actually want to understand anything about how the model works and how the process works, that's not really very satisfying. So the shortcomings of AutoML is that the sort of general AutoML solutions have a lack of domain knowledge, and um, that might result in less than optimal choices of pre-processing, feature selection, overfitting and complexity. Uh, these tend to produce overly complex models. And just a second. Oh, I just trying to get rid of something on my screen here. There we go. That worked. Um, and they often don't work very well on unseen data, and limited opportunities for customization and lack of control. Um, they're becoming increasingly sophisticated, but still have limitations in guiding the pipeline to solve a specific problem. And all of that's true, but I see it as the biggest problem is interpretability. The models generated by AutoML are largely black boxes that are hard to interpret, or at the very least, you don't know how they were arrived at, which could be a major downside in regulated industries.
Really? Yeah.
So semi-auto ML is really for bridging the gap. It's a middle ground where the power of automation is combined with the expertise of humans analysts. Instead of fully automating the process, it provides strategic checkpoints. And that's what we were really thinking about when we started putting Diviner together is can we, uh, check on how the process is going as it goes along. So our belief is that while automation can enhance efficiency, human expertise and insight are invaluable, especially in nuanced scenarios and in domain-specific problems. And of course, our domain is largely spectroscopy is the most common one for us. So we really want to offer choices that work well there. So semi-auto ML, singular versus model family. Traditional auto ML typically offers one singular best model from an optimization pipeline based on some predefined metrics. I mean, so what are you going to optimize on? Root mean square error, cross validation? Okay, there's one. Is there anything else you want to look at along the way? Well, we like overfit a lot, looking at sort of those kind of metrics. But anyhow, the data goes in and you do some auto ML and the model comes out. But in contrast, semi-auto ML generates a family of models, and understanding that the best ranked model might not be the right model for the problem. So the data goes in and we get a lot of models out. And this actually kind of approach grew as we were working with Diviner, and you're trying a lot of models and you begin to see that there are a lot of models that are nearly equivalent in performance. So you really wind up with a group of them that are all doing pretty well, and we sought to take advantage of that. And we'll be talking more about that later. But our goal is to produce a tool that significantly speeds up the development of quality multivariate calibration models. And we wanted it to be transparent. The analyst should be able to understand why the modeling choices were made and use their knowledge of the data and what's going on as an advantage compared to a black box approach. And our hope was that also you might actually learn something from it if you look at all of these models and review them for what's working and what isn't, what's helping your model, what isn't helping. But we call our approach Diviner. And so why Diviner? Well, Divine is to discover or locate something by intuition, insight, or supernatural means. Okay, it's not supernatural, but we certainly do think that you can use your intuition and insight. And of course, a diviner was a person who uh, would go out and look for instance, water, uh, like where to dig a well as a person with a diviner. And here you see a 15th century woodcut of a diviner with his divining rod out there. And for us, it's all of these modeling options that we have, which of those should we use? And okay, we'll attack that with the lambda, I guess. So the diviner workflow for regression. So this is our main interface right now that's set up. You load calibration and validation data, and it really does a grid search over pre-processing, cross-validation. Right now, it's just set up for linear regression to do PLS and multiple linear regression, elastic net models. And it also has an outlier detection module in it. We put it out there in PLS Toolbox and Solo 9.5, which came out last fall, something like that. I think it's been out there about 6 months now. So the pre-processing or the workflow is pre-processing, select recipes, subset for outlier detection. I'll talk about that in a sec. Um, the outlier detection calculates robust PCA and PLS models. We for years have had robust methods in our toolbox. It really comes from our collaboration with the folks at KU Leuven and their Libra toolbox for robust methods. And you can review or reject outliers and then calculate initial models with pre-processing recipes, view the results, and select models for further refinement. And then the ones that you really want to focus on, you can do outlier re-inclusion, variable selection with IPLS. Actually, these initial models, we use our automated variable selection on them. We find that variable selection with IPLS tends to do a little better than the automated, so we often use that in the refinement schedule and then choose final models to work with. So here's a example data set. This is a Tormod Nays and Thomas Isaacson data set that's been around for 30 years here. It's a full 3-component mixture design, casein, glucose, lactate. And we use that as an example fairly often. And this is the diviner output from that. Before I talk about that, I actually want to show you here that this is not vaporware. All right, it does exist. So just a second. There we go. So here's actually the diviner window right here. And I have this data set loaded up. But one of the things I wanted to show you here is that when you go to pre-processing, you get a box comes up with the pre-processing recipes that it's going to try. And so we have preset libraries of pre-processing recipes that are customized for certain things. So here's one for near infrared, mid infrared. And if I choose basic, that will give me kind of a short list of recipes that are used to test. And so it's uh, this is a list. I don't know how many are in here, about 20, something like that. Everything from auto scaling to using some derivatives to adding some normalization to doing some smoothing. And the check mark is whether that's going to be included in the current run. There's also this list here for outlier detection. Outlier detection takes a little bit of time So, but one of the things that's sort of interesting about outlier detection is that what samples appear as outliers depend on your preprocessing. For instance, if you have a baseline problem and it's only present to a large degree in a few samples, if you use a baselining approach, then those samples aren't outliers anymore. But if you don't, they are. So we try a few different pre-processing types to see what samples are consistently outliers. And that really helps you kind of figure out if you really need to throw something out of a data set or if you can leave it in. So this is the pre-processing steps. And I'm just going to say okay here. And you set up cross-validation in it. You can turn outlier detection on and off. And then after that, you just run it. And for the sake of time, I'm not going to do that right now. A problem of this size, the initial run takes kind of in the 3 minutes range on my fairly new laptop here. So I'll skip that part, but just kind of look at results. So um, here in this example, there were 77 pre-processing methods considered. This was one of the big ones where we use a lot of recipes. 20 latent variables, automatic variable selection on each model. And, this turns into something like 3,080 models real fast. And when you talk about how many models you have to calculate, it's actually quite a few. This is about 10 minutes worth on a MacBook Pro. And here are a couple of our favorite plots that we get out of it. I've talked about this at some conferences, which is this is the overfit versus error across validation plot here. And this is the ratio of the error of cross-validation to the error of calibration. What would a perfect model look like? Well, if you had a perfect model, then your error of cross-validation should be just a little bit more than your error of calibration. But if your model's overfit, then that ratio is going to get larger and larger. This, of course, is error of cross-validation on this axis. So you want models with low cross-validation error. These are models that are too simple to have a good error cross-validation. So what we're looking for is really the models that are down here in this corner. And also you can look at them on the test set and make sure that these models wound up down here in this corner also. And you want to check that. So there's a couple of things here about that, why this plot overfit less than one, why does that happen? That's a little bit here, and why we like this particular plot. There's some links to that. Anyhow, then you can refine them. You can take some models and then you can start looking at what is working and what is not. So here we're coloring these by whether they've had automated variable selection or IPLS or none. And you see here actually are ones with IPLS. This set of models is doing a little better. They're a little lower in cross-val and a little lower in overfit. So this is a good set of models. You can also look at, well, how many latent variables are in these models? What seems to be about right in this data set here? And so you can look at it that way. You can look at whether derivatives are working or not in this data. So here we see the red ones are first derivative, the greens are second, the blues are none, and the light cyans are smoothing. So you begin to get an idea of sort of what's working and what isn't in your modeling process here. This is using coloring them by whether they've used a baseline filter like a Whittaker filter. And this is what we really hope is that when you go through this, you begin to see what works and you learn something about your data. Okay, we can also look at what variables were typically included in the models that worked the best. So here we had 85 total models that we got this original group of 3,000 down to. What variables are they typically using? What are they focusing on in the spectrum? And we think that's useful information too. So the output, flexibility and diversity. It's an output, it's an aggregate of all the selected models through the diviner workflow. And at that point, once you've gone through all this, you can choose a single model, an ensemble of models, or a weighted ensemble of the top ranked models. And we think that user-driven model selection offers flexibility. Instead of just picking the best model, we can explore a range of models, increasing the odds of finding one that's both accurate and robust for deployment. And I appreciate you can gauge a little bit yourself about whether you think it's worth it to do a more complex set of pre-processing, say, for a small gain in error cross-validation or error prediction. So you have a chance to have input on that. And with that, so let's see, diviner output selection. These are 85 models selected. And one of my favorite features of it is we get this nice table out that ranks the models for us that you can sort the models then by error of calibration, error cross-validation, their overfit ratio, their root mean square error prediction on the test set. And you have a chance to look at them all together and really get an idea of, what's typical about the ones that are working best. So this table is kind of one of my favorite features when I'm in the modeling process here. And you can use various filters in it to not look at certain model types and et cetera to winnow down your selections. Okay, in this case, this is yeah?
I can take over here if you want me to.
I would love that.
All right.
Okay. Am I getting into your territory here, Manny?
That's fine. It's our territory.
Okay, are you ready to share your screen?
Yes. All right.
Man, I tell you what, I'm so tongue-tied this morning, but it is only 20 minutes after 6. So
yeah. Well, here in the East Coast it's 9:24, so I've been awake for a little bit.
Okay.
All right. So this is one of the outputs that we get from Diviner. One of the things that I really like is that basically you can export anything from here to the analysis window, and you can actually have a multiple selections and saved all these models that you have in your top rank together. One thing that I want to point out, though, is that these models are already performing really well. You saw at the beginning, at some point in the presentation, that the data set, it's really well behaved. It's a beautiful design of experiments. So there is no surprise there. So to begin with, it's going to be hard to improve over this. We are seeing that we have some models that are actually cross-validate really well, and they are not incredibly overfit or anything like that. So we are trying to improve here something that is already pretty good. Just keep that in mind as we move along and we talk about model fission. So the biggest question is, well, now that we have all these models, and you saw that we were making a selection of the top 85 models that we were interested in a run that started with 30,000, right? So what can we do with those models? Well, yes, we can certainly keep them, and that's what we traditionally do. A lot of the way the diviner works, the workflow is based on how we usually handle data when it comes new into our consulting efforts. So we usually try to find, what works for the data, and that's how. I mean, and now it is nice because we have a UI, and that helps a lot. It helps me. I don't have to be coding that much anymore. But that's one of the great things, that we have now this nice way to still have good information of what we are doing with the data, and build all these models. So, because I mean, the diviner presents us with this easy way to keep all these models and keep track of stuff. I mean, because one of the things that diviner does is that it's very memory efficient. So you don't have to save those 3,000 models in memory. They are not in your workspace. What we do is that we build them, we get the information that we want from them, and then we save every parameter that we need to rebuild them. And then when we call for them, we rebuild them in the process. And because these are linear models, it's not a big deal. So what we are going to do with Model Fusion is that we are going to take new data, and then we are going to apply it to all, let's say, 85 models we selected, that we showed before, that we selected. And we are going to ensemble those predictions. How we're going to ensemble those predictions? Well, there are a few ways that we could do that. The first instinct will be just to do an average, right? Or maybe get the median of the predictions of the model. And you can see here, for example, that on the right and at the bottom, we have what is the room square error of calibration when we take the median, and when we take the cross validation, and when we apply those models to the test set. And well, we can see that it's not doing better. What we have here on the left are the two best. From those 85, we have here the best performing model and the worst performing model. So we can see that, for example, for the cross validation, we are somehow in the middle. We tend to be a little bit closer to the best performing model. But for prediction, we can see that we are already doing slightly better. And remember that this is why I show you first that these are models that are already working really well. It is going to be hard to improve on that, but we can see that we can see here that we can have some improvement, at least in the prediction set, just by taking the median of those predictions. But one thing that we realize is, well, 85 models is a lot of models, right? I mean, it might not be super efficient. We also know that when we want to build this kind of ensemble of models, we start thinking more of baggier, right? How we can build, for example, thousands of estimators that are not super well fit, but then we can get a better result out of combining them and stuff like that. This is not the case, because we are really optimizing these models to be as good as possible. So 85 models might be an overkill. And we started asking, well, what is the easiest way that we can find a subset of these models that actually shows an improved performance? And we know that if we start trying to do an NHK and starting with just 3 models, we are going to end up with an insane amount of possible combinations, right? Because if we try to combine all the 3s, all the 4s, all the 5, it's going to be really hard. So what we have opted for is that we are going to be usually, or typically, we're going to be choosing between 13 and 15 models. And yes, you guessed right. It's usually the odd number, just because we are taking the median. So we want one of those results to be the actual. One of the results in the predictions to be the actual final prediction. But we can take even 17, and that will still be a reasonable amount of combinations. So this is what we call optimizing, the fusion models. And here on the right, we have a table with our favorite 15 models from those 85. We have root mean square of calibration, cross-validation, the prediction error on the test set, and the overfit ratio. Keep in mind that each of these columns, that lookup table is valid. So whenever you see a green color, that means that's the lowest error. And whenever you see a green color on the overfit, that means that is the closest to the 1-to-1 ratio. And here what we can see is that, when we take the median of that, the best error that we get in cross-validation is about 0.31. For the prediction is 0.2740. So we get already a good result. But what if we just take all those possible combinations? So it's about 32,000 models, because we are not saving the models per se, but we save the outputs of the models. We can aggregate those results very quickly. So calculating those 32,000 models, it just takes about 17 seconds on my computer. So this you can calculate very quickly. Now I'm going to introduce a new concept here. It's a new concept in the presentation. It's not new by any chance. This was introduced in 95. So it is called ambiguity, and it's just a measure of the diversity of the model ensemble. And what we mean by diversity is how much the models in the ensemble, or how different the models in the ensembles are respect to the prediction of the ensemble itself. And that's all that you are seeing here. So we aggregate those, we take the mean of those differences. And if you think about it, it's a pretty important concept, because what you want is ensemble of models that have very high ambiguity. You want the ensemble of models to be diverse, because if you have more diversity in your responses, what will end up happening is that if you have, for example, one of the models that is predicting high and some of the models that are predicting low, and if those high and low are very different, your model at the end is going to be able to produce a more accurate prediction, if you might, depending on where you are, in your reference. But we're going to talk a little bit more about that later. But the important thing here is that because you want the model with the highest ambiguity, it's very easy for us to pick what will be the ideal model. You want the model that have the lowest error of cross-validation with the highest ambiguity. So you can see here that from those 32,000 possible combinations of these 15 models, the model that we want is the one that is up here. And that's a model that has the model 5, 8, 11, 13, and 15 in this list. And you can see the error of cross-validation it's lower. The error of prediction is a little bit higher, but you can see that we can start improving in cross-validation in that way. Now, the one thing that I will say is that you could also plot, for example, the prediction ambiguity versus the prediction error. And that's something that right now is not implemented, but that's something that can be done. So you can make sure also that you have those two plots, just like we do with the output of Diviner. All right, these are another ways that we can add up the predictions of the model ensemble, right? We can fuse them also by weight them. In this case, we are going to just use the inverse of the cross-validation error. And what we're going to do is just calculate that and then softmaxing. The whole reason is because we know that the output of these models are going to be very close, right? These are all the best performing models for a certain problem. So in order to make actually a difference, I prefer just to normalize into softmax that is going to kind of emphasize the differences between those models, instead of just, if I do a regular normalization, it will work too, but it might not be picking in the nuance. And that was funny because, this is something that I keep saying that I have to correct. And that is that I just left here a couple of decimal spaces or 3, and maybe I should have another one so you can actually see that there is some difference between these weights. But that's one of the things that we can do, and then we can just aggregate the predictions based on those weights. And now you can see here that we improve a little bit compared to the medium. But again, we are just improving very little, and this is all because we have we are trying to make better already some models that are already pretty good. The one thing that I will say is that, well, I mean, I am not showing you here also what happens when you mix some of these methods, right? Like what will happen if I get the model fusion with the results of the optimization. We will leave that maybe for a white paper. The final method of fusion that I want to show you is stacking. I'm pretty sure that as you guys were going through the presentation, you were already thinking like, yeah, this is what we should do. So instead of just getting the predictions and doing a mean or trying to aggregate them with weights, what we're going to do is that we're going to use that output as an input for another meta model. And for this meta model, we're going to go use regularize MLR. The reason why we want to use elastic nets is because we know that all of these predictors are going to be, all of these features that is basically the output of the other models are going to be super highly correlated, right? So MLR, I mean, elastic nets, we like it because, well, first of all, we have the lasso component there. So we know that we could actually zero the contributions of some of these models. But the important thing is that now we are trying to weight these models in a little bit smart way, right? Because, I mean, the ultimate weights are going to be selected by the least square solution. So this is basically the ultimate way that we could do this. I think in the final release, with the PLS toolbox, we are going to also have the option of doing the regression with PLS. So, but you can imagine that that's a very low ranking system. So you are going to be arguing, well, I mean, should I include 1 or 2 latent variables? If maybe your data is non-linear, maybe you have a third degree of freedom. So that's the kind of stuff that I like about MLR, because even though you have to optimize for L1 and L2, that you can do a grid search, and that optimization is going to be automatic. All right, so these are the final results for the CGL data, that data that we started showing you. And what you're going to see here is results over different data sets. And what I'm going to show you on the left is the our favorite 15 models for that particular data set. We're going to have here also all the results for the fusion methods on those 15 models, including, for example, when we have the best ensemble. And we are going to show you here what the best ensemble is. I don't remember if I show the #1 ranked by test setting every single model, but I mean, it's easy to find because you can see the contribution. And here on the right, we are going to show the 85, like whenever we pick a bigger number of models. Very apparently, it's also very early for me today. So here we have 85 models. In other data sets, we are going to have more, or we are going to have less. It's just that sometimes we find in this overfit versus error plot that there are some cluster of models. So I prefer to just keep that cluster because, I mean, it seems that there is something common with them, at least performance-wise. The important thing is that, I mean, and this is kind of the underlying tone in that conversation about ambiguity and diversity, is that you will see that when these ensembles are successful, it's usually because we have a lot of different kind of preprocessing in them. All right, so the results for those are in the bottom right. And of course, there's no best ensemble because we are not calculating the 25 million combinations of 85 out of 85 models. But you can see here that we have the weighted and the linear stacked. So the weighted is the one that is weighted by the error of cross-validation, and the linear stack is the one that has the meta model. And you can see that when we compare to, for example, this is the best ranked by, it's a little except there because the best rank is actually 1.14. But in any case, the linear stack models, this is the overfit. So this is actually, still this one is lower. So I'm guessing, I don't know what I was selecting by, but I do have to fix that. But we can see here that our best grand model is about 2741. The error we have here with the median 2740. We cannot get, we can improve that by a little bit with the weighted by the error, but not really all that much. What we do see is that, for example, in this particular case, when we take the median of those 85, we seem to have actually a good, a model that is performing well in the test set. But you see the error cross validation is not that great. So, well, that is when you might be in trouble. Why we are gonna use. One note before I move on, because that is not part of this presentation, is that when I have talked about this before, the question that I always get is, well, all of these are linear models. What happens with interpretability? Well, this is one of the big problems. Interpretability basically goes out the door the moment that you ensemble all of these models, because now this is behaving more like a tree method. So interpretability becomes a little bit more cumbersome. And the best way actually to do it, I will say, is using Shapley values. But the fact that these models, the underlying models, the base models, are linear doesn't mean that we are going to be able to interpret easily the ensembles. But now we have what I will say modern cool tools like Shapley to do that. All right, let me move on now for the next one. This is SBR dataset, the styrene butadiene, and you're going to keep seeing this kind of trend. It is really hard to pin down exactly when when ensemble of model is going to be better, it's going to perform better as an ensemble. As a big ensemble like in the right, or a smaller ensemble. But the one thing that I can tell you is that I haven't found a case where you don't improve a little bit. I haven't found a case where you don't improve a little bit. I hope in my double negative, I keep messing this one up because I try to say it in an easy way, but apparently I haven't found a way.
In all cases, you improve by a little bit.
Yes, there you go. There you go.
That's the phrase you're looking for, I think.
Yeah, I think I will have to write that one down. So you can see in this particular case that, when you do the best ensemble, so it does seem to be indicating that using a small number of samples does help a lot with the error on the test set. While here you see that we have a very large errors when we try to ensemble 87 of those. This is the near shootout. And here again, you see some improvement. In this case, the one that seems to be winning is when we weight by the error of cross-validation. So we have a prediction error that is the lowest, very comparable to when we do the same thing on 79 models. Here is the near result composition, another standard benchmark data set. And we can see in this case, using the meta model, the linear stack actually has the best performance, both in cross-validation and prediction. And yes, I mean, those models were going to tend to look less overfit, but it's mostly because, we are stacking models on top of models. Decatur is a great example, mostly because we know that for fat, Decatur is nonlinear. So what we start seeing is that as soon as we start ensembling models, we start seeing errors on the level of nonlinear techniques. So, your SVMs are going to be, and artificial neural nets are going to be around this realm too. So that is kind of start to hinting on how that diversity, how that ambiguity in the model selection can help you. And in the case of nonlinear, I think it's where really that shows up a lot. And this is our final data set, and this is the Chemiometric 2018 challenge. And here again, we see that the lower numbers of error actually helps keeping the number of models low. And the linear stack wins here too. But I guess the reason why it's important that we go through different data sets is because we haven't found a rule. I don't think there is one. I think that you have to build these models and see which one is more useful.
Yeah, also let me comment on that chemiometry data set, which is that,
Yeah.
It's a whole bunch of different foodstuffs. And so this probably isn't the best way to actually make a model, but, we use it as a challenge to see, can you get a prediction for, I think it's protein, isn't it? That we're
Yep.
predicting
Yes.
here across all these foodstuffs. And this is actually a pretty darn good model considering it's going across all these types. So um, it's kind of interesting.
Yeah, I mean, and that's another thing that we know that the chemiometry data set, when we interrogate it in this way, that we are not separating by different kinds of foods, it also behaves non-linearly. And this again starts hitting in the same realm of the errors with non-linear methods. So that's why, we think that it was interesting to see these results. So do you want to take it away, Barry, or you want me to finish this?
Oh, I can talk, but why don't you just do the slides?
All right.
Yeah, key takeaways. Semi-autoML time saving. This automation accelerates model development because you can just have this preset list of all of the pre-processing recipes you'd like to try and just hit go, and it makes all these in just a couple of minutes. We also think that you gain some insight. You can see which things are working, what pre-processing methods work. Sometimes we see things like only pre-processing methods that include, something that would compensate for a scatter correction work. So that that's a key issue in your data set. Also, do they hone in on the same variables, and what's a typical number of latent variables in the model? I think that all of those are sort of useful information about your data set. So, we hope it gets you to good models and improves your understanding of the data at the same time. And then model fusion. Higher accuracy fusion models often achieve better accuracy than single models, but I think the more important thing is the robustness aspect. The ensemble reduces the variance. There's less prone to overfitting. It tends to be more stable on new data. And I just love the fact that when you use that, it doesn't force you to choose a single model. And that I think is the thing that I really like about it the best is why don't we use in some sense, the aggregate of our best models and not be forced to choose a single one. And what's the next slide?
But just before we move on, because I mean, I think that one thing that I didn't mention is that this is, I mean, the way that we handle ensemble models, it's already integrated in the PLS toolbox. So this is a model object. So any object that, just like any object you had before, to apply to new data, you just do .apply. So I guess what I'm trying to say is that this is really easy to take and deploy.
Wow, .apply, that's for all you command line geeks there. Yeah.
Yeah, sorry.
But we think that semi-autoML plus model fusion equals faster insights and better models. And
yeah, I think that's all we got.
yeah, well, the next slide.
Oh, the next slide is just extra slides for.
Oh,
for
okay. You don't have my finishing slide, which is
I
basically
don't.
no. What we say here is that it isn't to replace the analyst; it's to make the analyst better. Is our goal with Diviner, and it's not an AutoML that's going to make all the decisions for you. Instead, we've tried to create a system here that will make the analyst better, lead to some insights. The analyst has a chance to have some input and might actually learn something.
Very nice.
Yeah. So that's it.
Yeah, thank you.
Any questions?
Yeah, let's see if there's any questions. I do.
Gosh, I hope so.
Well, I have some, but let's wait and see.
Hi, I have a question. Well, first of all, thank you for the presentation. I think it's a really interesting tool because I have also a similar tool that I presented in this Monday's webinars like a year ago. If you remember, it's like for preprocessing stuff. It's just about the preprocessing part. But my question is that related to that, have you considered any indicators or any way of screening preprocessing methods to not try all the models?
You mean
yes. Go ahead.
Okay. No, you go ahead, Manny, since you answered that. Yes.
So yes, the problem is that it is really hard. We are still, we are baking a lot of things with Bayesian optimization, but it is not straightforward. And the problem with Bayesian optimization is that the surface response are all over the place. So it is really fine. It's really easy to find local minimums and get lost in there. And that's one of the things that has been extremely frustrating with using Bayesian optimization for preprocessing that are somewhat similar. So right now we believe that the grid search, and again, because these are linear models, we can live, with waiting for 3 minutes or 10 minutes. I don't think anybody, this is really saving people days of work. So when you think about it in that way, you realize that you don't mind waiting for the grid to calculate, the 3,000 models. And there might be other issues that arise when you are calculating that huge amount of models. And that is, well, I mean, what's going on with cross-validation, right? Are you going to find those 3 models that actually kind of cheat the cross-validation and look amazing just because, the sheer volume of models that you are calculating? Well, that's something that you will have to live with. There was a little reference there also, for example, to a case that we see when, sometimes the error of cross-validation is better than the error of calibration. I think Barry has a blog post for that because that's something that we're investigating. But yeah, we have looked into it. I guess the short question is there, but right now it's still a very early stages of development.
Okay, thank you. Because I'm doing the same, and I published a couple of papers on that topic. But yeah, I'm still doing it.
Okay. Yeah, well, the other issue here is what happens when you have a variable selection, and that's
Yeah,
when
yeah,
things
that's
is a little bit harder. Yeah.
Yeah, it's going to be really interesting when it gets extended to nonlinear models that take more time. But one of the things that we've found in the work that we've done on that so far is that if you get a good set of variables for and pre-processing in linear models, those are usually the better ones than the nonlinear models too. So um, our approach as we extend that is going to be to move forward with the results from linear models into a limited set of nonlinear models, because the computational time is going to go up by a couple orders of magnitude once you start messing with those.
Can I ask you, how does it work with the ensemble models in a regulated environment? How happy would they be about ensemble models?
Oh, probably not.
Yeah.
Well, no, but that's a great question, because the thing is that the same tools that you're using for a TensorFlow model, you're going to be able to use ensemble models. So if you don't like ANNDL, I mean a deep learning model, well, fair enough, you are not going to like an ensemble model. But if you're
Right.
allowing in your environment a TensorFlow model, then you shouldn't have a problem with ensemble models.
Right. And if, for instance, if you're using an XGBoost model, I mean,
Yeah.
it would be sort of the same, it's
Yeah.
oh yeah. So it all depends on your kind of level of comfort there. But I mean, that's one of the beauties is you can stop and just choose a final one and have one model and but along with it, the information about how it was arrived at. And I think that's a pretty powerful thing in a regulated environment, because you would wind up with one interpretable model and all of this thing to put in your notebook about how it was arrived at, about what works, what didn't, what variables are selected, all of that business. And I think that that's pretty useful for that environment.
Makes sense. I have another question. How often do you get surprised? How often do you learn stuff you didn't expect? Like, I don't know, autoscaling is nice on spectral data and stuff like that. Because now that you do comprehensive modeling, there must be some new learnings every now and then.
Well, the one thing that I was really surprised at when I started doing this was how often SNV followed by autoscaling works in spectral data. I had no idea.
No.
And so yes, we do get surprised sometimes that things work that maybe you wouldn't have guessed. And that I think again is the beauty of it, because if you're making models one at a time, uh, you tend to use the things that you think are going to work, and you don't have months to do it. So this hits a lot of things you wouldn't have tried.